All right, welcome back. This is part 4. Sorry about the length of this video, but it's an important chapter. So we're going over the multiplication law. That's where we left off. The probability of A intersect B is equal to the probability of B times the probability of A given B, or we get the same answer, probability of A times the probability of B given A. So an easy way to remember these formulas is that you have to remember that whatever you put first here, this single probability of B in this case, that the order of the conditional probability is that whatever's here, that has to be given. It's occurred. What's the probability that something else happens given, in this case, that B happened? So you can see here, you can do it B, probability B, times the probability of A given B, or the probability of A times the probability of B given A. You can see right here, probability of A, this conditional, A is the given. Probability of B is here, B is the given in the conditional probability. And here we have Markley Oil and Collins Mining again. We want to know the probability that both of them are profitable, that Markley and. That word and is key to multiplication. If it's or, you know you're going to use the addition rule. The word and is important. That tells us multiplication law. So the probability that they're both or Markley and Collins are profitable. The probability that Markley is profitable was 0.7. The probability that Collins is profitable, given that Markley is profitable, we calculated earlier, is 0.5143. So if we knew those two, but we didn't know the probability of M intersects C, the probability that Markley and Collins is profitable, we could use this information to get that answer. The probability of M we know is 0.7. The probability of Markley given Collins is profitable is 0.5143. Multiplying those together, this is reversed. This is a mistake. This is the probability of Collins given that Markley is profitable. Okay. We have an M here. So M has to go here. This is a typo. That is the correct form. C given M. And that was 0.5143. We knew that from the previous problem. Multiplying those two together, we get the 0.36, which is exactly what we were given in this problem. So you can see here, we were given this and needed that in this problem when we did earlier conditional probability. When we want the probability to intersect, we don't know that yet. Even though it was in that previous problem, in this problem, we don't know it. The next thing we have is a joint probability table. Here we have Markley Oil, profitable or unprofitable. Those are the rows. The columns are Collins Mining, profitable, not profitable. Okay. So the profitable, Markley Oil is profitable, M. There's a 36% probability that Markley is probable and Collins is probable. 34% probability that Markley is profitable and Collins is not profitable. And if we add those two together, you can see we get the 70% probability that Markley is profitable. Going down here, if Markley's not profitable, we didn't work on any of those. You can see that's M superscript C. That is the complement to profitability. You're either profitable or you're not. Breaking even would probably count down here. Profitable, that Markley that Markley is not profitable and Collins is, there's a 0.12 probability here. The probability that Collins is not profitable and Markley is not profitable is 0.18. Add those two together, you get 0.3. There's a 30% probability in general that Markley is not profitable. Now to check your work, you add your column and your rows, and you should get 1. That's all of the probability. Okay, joint probabilities appear in the body of the table. These are joint probabilities. Marginal probabilities appear in the margins of the table. These are marginal probabilities. The next thing we've got to look at are independent events. An independent event is if the probability of A is not changed by the existence of event B. We would say that A and B are independent events. Now, if two events are independent, the probability of A given B is just simply equal to the probability of A. To give you a simple example of this, the roulette wheel. In Las Vegas, they had a problem with people not playing roulette games. So the managers of the roulette tables came up with an idea to get more people to play roulette. They said more people will play roulette because they'll think they have a better chance of winning if we put a board up. Then this board might have the results of the last 10 spins. Okay? So every time you go by the table, you see the numbers that came up on the last 10 spins. People think that the spins are dependent. Some people do. I remember I used to hear gamblers tell me all the time, I'm from Las Vegas. They would tell me all the time, oh, whatever the last number was, make sure you bet it because it always comes up in twos. So if a 10 came up last time, bet 10 again. So if that were true, you would be saying that the outcome of A, the probability of A, another 10 coming up, is increased if a 10 came up on the last roll, and that would be B. In reality, all of the spins on the roulette wheel are independent. What comes up now has no relationship to what the last number was. So the probability of a 10 coming up is still the same as it was before, no matter what comes up. 1 in 38. There are 38 spots on a roulette wheel. 1 through 36, and then 0 and 00. So in that case, this board doesn't help you win at all because this spin and the last spin are independent. People think they're not, but they are. So in this case, the probability of a 10 coming up, given that a 10 came up on the last roll, is simply the probability that a 10 comes up, 1 in 38. It isn't influenced at all by what the last spin was, B. The multiplication law for independent events. The multiplication law can also be used as a test to see if two events are independent. The law is written as the probability of A intersect B is equal to the probability of A times the probability of B. So here, let's say that A and B are both, they're both a 10 coming up. A 10 coming up on this spin, and a 10 coming up on the last spin. The probability would be equal to 1 over 36 times 1 over 36. So the probability of getting 2 spins on of the same number is 1 out of 1,296. It's 1 over 36 squared. We're going to skip through some of this. Mutual exclusiveness and independence. Do not confuse those two events. Two events with non-zero probabilities cannot be both mutually exclusive and independent. If one mutually exclusive event is known to occur, the other cannot occur. Thus, the probability of the other event occurring is reduced to 0, and they are therefore dependent. What this means is, let's say we have a car. A car can be broken, cannot work, or it can work. It can need repair or not need repair. So the probability that if a car needs repair, the probability that it could not need repair is 0. So those two events are mutually exclusive. Two events that are not mutually exclusive might or might not be independent. But if one mutually exclusive event is known to occur, the other cannot occur. Thus, the probability of the event occurring is reduced to 0. You can't have a broken and a not broken car, because those two events are mutually exclusive. The last thing we have here is something fairly complicated. It's called Bayes' theorem. I've got a video on this, and this one's running out of time. I don't have enough time to finish that. So if you're having issues with Bayes' theorem, just watch the video that I've posted already on Bayes' theorem. Thank you very much. Have a great day.